Hi, welcome to another edition of Calculus 3. Today we are going to talk about tangent and normal vectors. Let's go see the story of this topic. So, tangent and normal vectors. If I am on a trajectory, well, at each point I am traveling in a certain direction. That direction is going to define my velocity and the tangent vector. So I have a certain vector here, that would be the velocity vector, and along this I'm going to choose a vector that's of unit length, and I'm going to call it the unit tangent vector. So I'll have some vector in the direction of v of unit length, that is, I'm going to call it t. Well, you have noticed that when you go around a corner on a bike or in your car, your body leans in a certain direction. Well, that is more or less the normal vector that we have in mind. That there is another vector here. We are going to call it n. And we want to describe this vector as well. We want to find formulas for t and n and a variety of other things. And let's go and start by looking at the picture we have seen before to make sure we understand what is involved here. So let's go after this nice software that we have here. So here I have written an example of a curve in space. The x component of it 2 cosine t, y component 2 sine t, z component is 0.1 t. So it's kind of a helical picture, this colorful picture that you see here, like a spiral staircase. Sometimes you see something like that around oil tanks and such. Okay, as you travel on this, or as a particle goes on this thing, you have a certain velocity. The velocity is going to be in the direction of tangent to your vector. If we scale this so that its length is going to be 1, that's going to be our unit tangent vector. And then out of this we are going to extract something else. It's going to be called the principal unit normal vector. That's in this blue direction. So to get this kind of a curve here, so first of all you want to define for yourself some space curve, that's r of t, that's going to have several components. And then once you have that, you can come and display a variety of things on that by looking at this curve setting and see what is it that you want. So for example, I might be interested in tracing the point itself. So you see kind of a bold dot here that's tracing the point, and I could ask, for example, for velocity, acceleration, and so on. I could ask for the unit tangent vector. Let me take that thing off. So the purple one is the unit tangent vector, and this blue color is a unit normal vector. We are after describing these two. So they're actually a triple, but right now we are going to look at these two as the big news here. So let me go around so that you see more of this as I go around. You see the tangent, unit tangent, well, is tangent to the curve. And the normal vector, you see, is pointing toward the center. For this kind of a helical motion, the description is rather simple, but in general it can be quite daunting to find these things. Let's go ahead and learn how to do this thing by hand. So we come back here and let's pick a simple curve to play with. So previously we said we have a r, or r of t. Typically we use this thing to represent a position, or position of the particle in space. And then you remember v was dr dt, and to keep our writings shorter we just call it r prime. That was of course our velocity. And we had the third one of this trio, a was dv dt, or v prime, That was, of course, or we can call it r double prime. That was our acceleration. The only difference between here and calculus 1 is that over there this was just one item. Now if we are in space, it can have 2 or 3 components. Let's pick a specific example, see what we are looking for. So suppose I have r in space, t squared, t cubed. Simple example. This is a trajectory in space. What do we want to find? We want to find, so given this space curve, we want to find let's say velocity, and say unit tangent vector, and evaluate them at, say, a specific time. Let's say t equal to 1, and find the equation of the tangent line at this point. So I practice from calculus 2, find the equation of tangent line at t equal to 1. So the only thing here is, well, what do you mean by unit tangent vector? Well, when you're traveling on a curve, your velocity vector is tangent to your curve. So unit tangent vector, unit tangent, it's usually shown by t. As you go around at different times is different vector, but to keep it simple we just call it t. That is simply this vector normalized so that its length is 1. How do you normalize a vector? Well, if you have a vector, if you divide by how long it is, so the length of a vector we showed by v in absolute value. In your text it puts double vertical bars, but we said it's going to make our writing very crowded, so that's good enough. So a vector divided by its length is going to be a unit vector. So that's our unit tangent vector. So how do you find it? Well, let's go step by step. First of all, how do you figure out velocity? That's very easy. Velocity is the derivative of position, and with derivative you just differentiate. It's just that you have to do it several times, 2t and say 3t squared. You remember we said you have either this notation or you can use the following notation, a little bit more crowded. So this I, j, k where are unit vectors in directions x, y, and z axis. So that's our velocity. This velocity changes as we go around. So this at time t is equal to this. How about at time 1? At time 1, well, at time 1 your t is 1, so you're left with 1 and 2 and 3, so that is going to be your velocity vector at time 1. What if I want to find the unit tangent vector? So unit tangent vector t at any time t is going to be v divided by how big the v is. So v is still 1, 2t and 3t squared. And you remember how to find the length or the norm of a vector. That's just like a Pythagorean theorem. These are the sides and you're calculating the hypotenuse or the diagonal. So 1 squared, 2t squared, and 3t squared squared. So it becomes 1, 2t, and 3t squared, and denominator, well, some expression, 1 plus 4t squared and say 9t to the 4. You notice the denominator is a rather complicated function there. That's what makes the rest of this topic a little bit hard in terms of algebra or the formulas. How do we get around handling this kind of expressions? In long term, we have to take this thing and differentiate it again, and so some of the formulas you are going to see later on is to simplify this task. But right now our job is not hard, because that all that we are asked is what is the unit tangent vector at time equal to 1. So at time equal to 1 your velocity is just 1, 2, 3, and then you divide it by a number so that this will be of length 1. Well, of course 1, 4 and 9 makes it what was that, 14. So 14 is the length of this vector. When you divide them, you have made a vector of length 1. One refresher from equation of tangent line. How do you write the equation of a tangent line? Let me just remind you. If you are at some point in space, let's call this thing say r0, and then you have a guiding vector or direction vector. Let's call this direction vector, letter D for direction vector. And then you're asking what is the line that is passing through r0 in direction of D. So, well, what is that? Well, you want to give an address of a certain location R on this. So you want to get the location R, you say start at r0, first go from the origin to r0, then take so many steps of this direction vector to arrive at your step. How many steps you want to take? Let's call the number of step S, whatever that is, times D. That is, so many of these yardsticks is going to take you to your destination. So okay, this was equation of line in calculus 2. So what is R? R is x, y, z. Who is r0? Well, is your starting point. So this is R means wherever you want to be in 2 or 3 dimensions. R0 means, well, you're starting at certain location. Give me the address of that location. Then there's a parameter. This parameter indicates how many of these yardsticks are we going to use to arrive at your destination. Typically you use a t, but since t has another meaning here, to stay clear of that, let's call this one S. And D is some vector with components, so it will have 3 components, typically say A, B, C, or whatever you have, and that would be equation of line. Sometimes they ask you, say give me x, y, z separately. Well, in that case you'll have x is your starting value, x0 plus whatever you call for your parameter times a, and then y is your starting value and the name of the same parameter times b, and z same way, so z0 plus s times c. So tree style vector format, and this one sometimes they refer to it as a parametric equation. If you're entering it on WebAssign, you just put a comma between these 3 components. The question that we are having here is, well, give the equation of that tangent line. So tangent line at t equal to 1. Well, this is the location at t equal to 1. You're at the location 1, 1 squared, 1 cubed, which is just 1, 1, 1. And then you are going in a direction of this vector 1, 2, 3, and then you just take so many steps of this. So equation of tangent line for us, equation of tangent line, well, has 3 components, x, y, z. At time t equal to 1, where are you? At time t equal to 1, well, this is my position. At time equal to 1, I'm at 1 squared, 1 cubed. Very hard to calculate, huh? So that is 1, 1, 1. And then I take so many steps in the direction of my tangent vector or velocity vector. Velocity vector is going to be easier to use. You could use either of them. So 1, 2, 3. You could have used that one too, but that just make it a bit more complicated. So 1 2 3, so 1 2 3. So what's the formula? So this is r at whatever time you want, let's call it t0. This is your variable s, and this is velocity at the same time. When you add them up, you get r. This is r of the tangent line, so its parameter is s, or whatever parameter you used here. Okay, so we did a quick review of Cal 2 on how to do equation of a line, and here we applied it to our tangent line to a curve in space. Next up is the more interesting aspect, which is what is this other vector. We said when you go around the corner in your bike or something, your body leans in a certain direction. We are trying to capture that direction. Notice we're going to use a special name, rather lengthy name for this thing. We're going to call it principal unit normal vector. Kind of a mouthful there, so if you want to make an abbreviation, maybe PON V, I don't know if that's a good abbreviation. So we want to find a PON V. What do you mean by principal? What is this doing? What do you mean principal unit normal vector? Well, normal. First of all, what is normal? Let's suppose we are on a trajectory like this, going up or down. Let's go up. Suppose I'm going up here. So we said we have a tangent vector. Okay, tangent, it's kind of obvious what it is. That's like if you are on a bus and you're going direction, your bus is like a vector, and that is your tangent vector to your trajectory or trip. A vector of length 1 on that will be your tangent vector. Velocity vector and tangent vector, they are all in the same direction. Okay, normal vector. Normal means normal to this. Well, there are plenty of normal vectors to a given vector. In fact, all of them together make an entire plane here. Like these are all normal vectors to this vector. All you are caring for is the angle between the two of them has to be 90 degrees. Okay, we are going to specify, first of all, unit normal. So I want the length of it to be 1. Well, okay, length of it 1, still I have infinitely many of these things. Which one of them do you want? Very qualitatively speaking, what you want is the one, the direction that your body is leaning when you are going around the corner. There's a particular one we are after, not any one of them. Then there's one that stands out. Let's call this one, I'm making it to go along with my T here, so let's color the T also. These are supposed to be of length 1, and T is in a direction of tangent to our trajectory. N is a particular normal vector, we call it principal unit normal vector. How do we find these things? Well, notice something from the previous lecture. So we are trying to capture N. This T, you remember, we said is of length 1. T, by definition, is of length 1 because we divided it by its own length, velocity divided by its own length. So T is going to be of length 1. In the previous lecture, we noticed that if a vector is of length 1, then it's going to be perpendicular to its own derivative. That is, T is perpendicular to, no, it's going to look strange, T is perpendicular to T prime. Quick reminder, if T is of length 1, it means T dot T is equal to 1. Now if I go ahead and differentiate it, derivative of the first times the second plus the first times the derivative of second, derivative of 1 is 0. On the left hand side, these two are the same thing. Twice t prime dotted with t is 0. So t prime dotted with t is 0. So a vector of length 1 or a constant length is perpendicular to its own derivative. Now it so happens that this main vector that we are after, that the way your body is leaning typically, this is going to come out of this t prime. The only thing is that this is of some arbitrary length. If you want to make it of unit length, we have to take this and divide by its own length. So this is our definition for n. n is going to be t prime divided by the length of t prime. So that I don't want to write that mouthful again. The pun v we are after, n is t prime divided by length of t prime. Let's go ahead and do an example so that we take the mystery out of it, and then we are going to do heavy duty calculations a little bit later on. Let's do an example that is cooked so that it's kind of artificially generated so that it wouldn't be too complicated. So we are going to take R, perhaps not too artificial, because it's going to look like actually that helical movement that we had. That's obviously not artificial. Many things are in that kind of a design. And so let's go ahead and take something like that. So I'll have R is equal to, let's say, cosine of 3t, sine of 3t. You remember the combination like this means you're going around the circle. And now let's add to it some vertical movement as well. Let's call it 4t. Okay, that's a nice set of numbers. Next up, what's the velocity? Velocity, well, velocity is just r prime. Just have to take a derivative. Just do it just 3 times. So minus 3 sine of 3t, 3 cosine of 3t, and this one will be, of course, just 4. Next up is, well, that's my velocity. What's my speed? Well, speed is going to be absolute value of velocity. Absolute value here is lucky day, because I have to square this, square that one, and square the last one. So of course I get 9 here and 9 here. So square root of, it's 9 sine square of 3t. It's 9 cosine square of 3t plus 16. Of course, 9 sine square plus 9 cosine square. What's that? What's this total? What is it? Of course, it's 9. So 9 and 16, and isn't that lucky that everything just so nicely comes out? And most important thing is that speed is a constant. So if you're traveling on this spiral according to this formula, your speed is a constant. Speed is like this. Okay. Then what did we say what t is? T is normalized velocity. So velocity divided by speed is t. T velocity divided by speed is t. So our velocity was this, our speed is that, ratio of the two of them, minus 3 sine of 3t, 3 cosine of 3t, and 4 divided by speed. Well, you might as well write everything inside. 3/5 of sine of 3t, 3/5 cosine 3t, and 4/5. Okay, now before going any further, this is really special that this denominator became so friendly and such. In general, the denominator is going to be a horrible expression with some t's and radicals in it, and next step typically is not so fun. but here it is t prime. Why do I want t prime? Because, well, we said n is t prime. How does your unit tangent vector changing in divided by sound length? So I have to find derivative of this. Not any more complicated than what we just did. Derivative of this is going to be minus 9/5 of cosine of 3t. That one also becomes minus 9/5 of sine of 3t. The last one, since it's a constant, it drops out. So this is how tangent vector, unit tangent vector is changing. The length of this, we get lucky again, the length of this, square of that plus square of that, maybe I should write it, minus 9/5 cosine 3t. If I square this and minus 9/5 sine of 3t and square that, and well, there's 0, it doesn't need to be there. Well, sine squared plus cosine squared again becomes 1. 9/5 gets squared, becomes positive, and then comes out is just 9/5. Okay, you go ahead and do that. Make sure you follow that. Now, if I take t prime and divide it by absolute value of t prime, this divided by that, of course, 9/5 goes away, and we get minus cosine of 3t and minus sine of 3t, and 0. Who's this? Well, by definition, this is our principal unit normal vector, or n. We notice that you can pull a minus out, minus say cosine of 3t, sine of 3t, and 0. Who is this? Aside from this, putting this aside, turn this 0, this was our position vector. The negative of that is the normal vector. It's very similar to what we saw here. Again, okay, position vector. What's the position vector? Let's go choose position vector for display. Here's called position vector. It's called trace vector. Trace vector. So this is the trace vector. That's the same as r, and this is the unit normal vector. You see that it's in the opposite direction of the r. If we go at t equal to 0, they are going to actually the angle between them decreases. I'm supposed to stop at t equal to 0. I made a mistake. Okay, this is t equal to 0. You see, this is the position vector, and the normal vector is just exactly opposite direction of that. That is what we are discovering with our own calculation. Okay, now let's move on to more advanced stuff. Next observation, of course, you notice that much of the stuff that we are doing here is going to be exactly what you're going to do in your mechanics class, or mechanics or dynamics classes. They are going to cover exact same thing. So it's good that you are seeing it twice, but of course it's also significant in mathematics all by itself. Next up is, well, we have talked about position and velocity. As of now, we haven't talked about acceleration. What is acceleration doing with respect to all of these other things? First observation that we are going to do is that acceleration is on the plane of t and n. In fact, if you are going on a circle on a constant speed, what's going to be your acceleration? Those of you who have taken your physics 1 or just from your bicycling around town and such, what would be the direction of the force that you feel if you go on a circle at a constant speed. Of course, your acceleration is going to be in the direction of n. Now, in general, if you go on an arbitrary curve, or if you're on a circle but you go at a variable speed, you're going to have an acceleration that is a mix of this n and t. The acceleration vector is going to sit in the plane of n and t. That's an important observation, an important selling point of what n is. There's no doubt about what significance of t. Well, that's the direction of your travel. But we call this thing principal unit normal vector, meaning in some sense it stands among all the other normal vectors. And the first point of significance is that, well, a combination of these two is going to determine for us what the acceleration is going to be. Acceleration is sitting in the plane of these two. Let's go ahead so here is an observation that we are going to have, or sometimes you call it a theorem if you want to make it mathematical. So we have an observation here, very significant observation, which is acceleration A is in plane of t and n. Okay, unit tangent vector and principal unit normal vector. The combination of these two is going to make what A is. Okay, let's see how does it go. We said t is velocity normalized. We are going to start from this and quickly see that the acceleration, let's put an arrow on top of these things so that it doesn't look like they're just letter A. Okay, so what can I get out of this? I can get velocity is equal to my tangent vector times speed. Physically, this is very understandable. Mathematically, it looks cryptic. This is my velocity. This is the direction I'm traveling. This is my speed. Speed times direction is just same as velocity. Well, what do I want to do with this thing? Well, I want to get acceleration. Acceleration was what? Acceleration was v prime. Okay, and I want to take a derivative of this thing. You remember in the last lecture we said differentiation has essentially same properties as it had in calculus 1. Here you have a multiplication of a scalar and a vector. How do you differentiate it? Well, first times second plus second times first. So I'm going to write t prime first times the second, and then t times v absolute value prime. Okay, t prime, where did that one show up? Remember we said n was t prime over absolute value of t prime. That was the definition of our principal unit normal vector. So I can say that t prime that I want is same as the normal vector times absolute value of derivative of the tangent vector. So let me put it back here. So instead of t prime, I'm going to put n, and then I'm going to have t prime, and then v. So instead of this, let's write, instead of this, I'm putting this one, and then this one I just leave it alone. We are essentially done. This looks rather cryptic as to what it is, but actually what we have is the normal vector times some number. This is the number is multiplied by, which is actually a positive number. A positive is just some positive number. And here is the unit tangent vector times something else. So essentially we are showing A is made out of n and times a number and plus t times some other number. That is exact proof of what this statement is, that the acceleration is a combination of n and t. There's nothing else There's nothing, for example, perpendicular to these two that's going to come in the expression of A. So what we do is that we say, okay, these two, we are going to give them names. What names is good to give them? Let's go ahead and draw a picture so that hopefully that resolves it. Suppose this is my acceleration vector. That's my acceleration vector. And let's say that this is my tangent vector. This tangent vector, and let's color this one some different color. So let's suppose this is, of course, they're supposed to be same length. This is supposed to be, say, my normal vector. If I want to write A as a combination of T and N, well, what am I doing? I'm just doing a very basic thing that you do in calculus or in all of your engineering classes. You find a component of this thing down here and another component of it over there. So what should I call this one? Well, this is the component of A alongside T, so it makes sense to call it A sub T. What would be a good name for it? That would be tangential acceleration. Acceleration that's in the direction of tangent to the curve you're traveling. Or what should this one be? Well, that better be called AN. That's the acceleration that's perpendicular to the direction that you're traveling. This is the force that is making you bend when you're turning around the corner on your bicycle or something. This is the thing that you have to watch out for. So who is this one? This is A sub T. And who's all of this? Well, all of that has to be A sub N. So we have the following two designation. A sub T. A sub T is going to be tangential acceleration or tangential component of acceleration. So here a formula for it is V prime. A sub N, who's that? That's normal acceleration or normal component of acceleration. Who is that? Well, the formula for it here is the following. Now there are many different versions of writing these formulas, some of them easier than the others to implement, but we have these two formulas. Well, let's derive some of these formulas. The first one is rather straightforward. If you have acceleration A sub T is the unit vector A. If I take the unit vector A and dot it with T, I'm going to find its component in this direction. So that is A dot T. Well, what was T? T was V over absolute value of V. So here's a more practical way of calculating this thing. Calculate your acceleration, calculate your velocity, dot the two of them, divide by speed. That will do it. For A sub N, we have a simple formula as well. Let me write it and then I explain it shortly below. I want to find this other component. Several ways of doing it. This is one way that will help you get it out of R, V, and A, which is the following. You take the acceleration A, now you have to cross it with the vector V, calculate the absolute value of that, and then divide all of that with your speed length of V. This type of formula is typically more practical than the ones that we have on the other side. Let me go ahead and explain this thing shortly. So remember in from calculus 2 or linear algebra or your physics class. If you have this, let's call the vector A again, and this one, let's call it in the direction of our tangent vector is going to be v, and the other one, well, the other one we just vector n. For the moment, let's call this angle here theta. When you are finding the component of this thing a sub t, if you pay attention to this triangle, what do you say? You say a sub t is equal to length of A, that's the hypotenuse, times the cosine of that adjacent angle. Now if you take this, multiply and divide with the v, well, in the numerator you have length of A times length of v times the cosine of the angle between the two of them. Who's that? Well, that's a definition of the dot product, A dot v. Denominator is just speed. Well, that's an indication of this formula. Now let's go ahead, look at this other triangle here, and this component, let's call it a sub t. Well, how do you calculate a sub a sub n? This angle is still theta. A sub n is going to be length of A times sine of theta. Again, I do the same thing. I multiply by length of v divided by that length of v. What is length of a vector times length of another vector times sine of the angle between the two of them? Well, that's the length of the cross product of those two. So A cross V, all of that divided by speed, is going to give us the formula for A sub n. Okay, there are some other alternate formulas for vector n. Perhaps I put it in another lecture, kind of an optional additional lecture that is a little bit more complicated than what we have done. But remember, we have these two formulas, which are, let me write it so that we can kind of put them in a box. Kind of celebrate them as our achievement for the day. These are tangential component of acceleration and the normal component of acceleration. They are two formulas that are going to help us with some basic problems in this section. So again, we need to practice these things and then we'll be good to go. The next section is going to be somewhat more complicated than this, and so we want to practice these ideas. Okay, until then, good luck and God bless.